Welcome. Today I'm going to talk to you guys about our next topic in our list. We started this series by talking about how you know where something is located, and then moved on to how you know whether it's moving or not. And then we talked about how you know how to measure that motion. Well, the next question I would ask you is motion always constant? And the answer, of course, is no. And so we need to be able to measure changing motion. And the topic for that is acceleration. So we're going to jump right to it. This is video 010 on acceleration. Okay, first, how do we know if an object's changing? Well, I want to draw out three possible scenarios for you, and I want you to think about what each would mean. Okay, so let's take a look for a second at this particular idea. Let's imagine a strobe light. And a strobe light, if you're not familiar with it, is a light that flashes at certain frequencies or certain intervals of time. Uh, Physicists like to use strobe lights because it helps your brain take almost like take pictures of certain instances. And then you can use those pictures to kind of compare what's happening in different scenarios. So I want you to imagine for a second we have three scenarios. So here's scenario number one. And I'm going to use a horizontal surface and a ball for each of these. So situation number one, at time one, we have this position. And then as the strobe light goes dark and then comes back on, we notice that the ball is now at this position right here. So again, we've got time one here and time two there. Okay. Now the second scenario is very similar, but slightly different, as you'll be able to see. So here's the second scenario. Again, we have a horizontal surface, as best I can draw it there. And again, the ball starts at this position right there when the T1 flash goes off. Okay, so we'll call this X sub 1 as well. When the T sub 2 flash goes off, we notice that the ball is right here. So this is its X sub 2. Okay, and then the third scenario looks like this. Like so. The ball starts at the T sub 1 flash right here at X sub 1. And then we notice that the ball is here at the T sub 2 flash. Like so. Okay. Again, this flash takes place, this image takes place at the T sub 1. And then the T sub 2 flash, we see this ball here, and that ball there. So my question for you is, what can we infer about the speeds of each of these objects? Well, let's think about it for a second here. What is the speed formula again? That's our 2.1 formula, if you recall. 2.1 looks like this, right? The average speed is equal to the displacement divided by the change in time. Okay, now wouldn't you agree that as I'm looking at this, the change in time for each interval here is exactly the same? I hope so. You can see this was all taken at the same time, and then these three were taken at the same time. And so the delta t for all of these should be the same. So I'm going to go ahead and write same there so you can see that. So don't forget that. Okay, so then my next question for you is if I'm going to calculate out the speeds here, I have to be able to figure out the displacements. And so, as you recall, the displacement is just the delta x. It's the change in the x position right here. So I'm I'm going to go ahead and draw like so. That's the delta x for this black drawing right here. Here's the delta x for the red drawing, the displacement there. And here's the delta x. Not my best arrow ever, but that's okay, for the blue drawing. And so my question for you is, which object has the biggest speed? Okay, would it be scenario 1, where you have a medium amount of displacement, scenario 2, where you have a small amount of displacement, or scenario 3, in which you have a large amount of displacement? Hopefully you can see that the answer, since the displacement's on the top of the fraction, and this is all the same for all of them, should be that this has the highest speed. So I'll go ahead and write that down. This is the highest average speed. Which one has the lowest speed then? Well, as you can see, the lowest speed has to be the smallest displacement in the same amount of time. And so I'm going to go ahead and write down that this one has the lowest speed. Now, why am I comparing three different situations? Well, because what's going to happen then is that we're going to have to analyze the motion of actual objects and see if the speed is changing. And so I'm going to erase this in just a minute and draw a fourth scenario in which we'll take a look at one object as it goes through multiple flashes on our strobe light. But keep this in mind, right? The change in displacement at the same amount of time is going to help us to tell what the speed is. Okay, so now let's imagine a new scenario. And this new scenario looks like this. Okay, so here's our surface. Let's imagine it's horizontal, because I do my best to draw that out. And that surface then, on it, we have a ball. And in the first flash, we notice that the ball is right there, x sub 1. In the second flash, we notice the ball is right here, x sub 2. Now remember that the flashing of a strobe light occurs at equal intervals of time. So the next interval of time, the next flash on the strobe light, we end up seeing that the ball is right here as it's rolling along. So this is our x sub 3. Finally, the last flash, we notice that the ball got all the way over to the side here. That's our x sub 4. Okay, now I hope you would agree that the change in the time for each of these, the time interval, if you will, is the same for all three of these changes. So the change from here to here, the change from here to here, and the change from here to here. So we have three changes, right? So what we can do then, if the time interval is the same, is we can look at the displacements. So here's displacement number 1. So I'm going to go ahead and write delta x sub 1, 2, so that you know it's going from position 1 to position 2. The next one is from 2 to 3, so I'll go ahead and write that like so. Delta x sub 2, 3, again, so you know it's going from 2 to 3. And then finally, let's do delta x 3, 4. So you can already start to compare the displacements. Obviously, the displacement for 1, 2 is smaller than the displacement for 2, 3, and 2, 3 is smaller than the displacement for 3, 4. What does that imply about their speeds? Well, hopefully you see that this has a very small speed here. This has a larger speed. And my pen is goofy again. And then this is the largest speed. Sometimes it helps just to draw very slow. There we go. Largest speed. So you can see that the speed starts off small and becomes larger and larger and larger. That idea of a speed changing in that way has a special name, and that special name is an acceleration. And so this brings us to the next idea. So there's three basic ideas that go along with all motion. The first one you learned was displacement. The second you learned was speed. And the third that you learned is acceleration. So there we go. Okay, so hopefully that makes sense for you. Now let's go ahead and move on to the next slide. How can we measure it? Well, we're going to go ahead and measure it here using our next equation. So this is equation 2. I'll switch my colors here. So equation 2.3 is our next equation on the formula sheet. And it has a very similar type of format to one that you've already seen. And it says the average acceleration is equal to the change in the velocity over the change in the time. Or if you wanted to be more specific about it, if you wanted to write it out a little bit more thoroughly and you're not as lazy as I am, you can always go ahead and write v sub 2 minus v sub 1 over t sub 2 minus t sub 1. It's the same either way. This is just the lazy version of it, so that's what I tend to write. So going back to our situation before, you can see that the velocity did change. It started off small, and so we'd have a small number here, and then it became bigger later on, so we'd have a larger number there. And so you could see that there was an acceleration. Now, that's really all there is to it. It's really that simple. I want you to point out, though, that this is an average acceleration. It's not the acceleration at any one particular time, but it's the acceleration that an object experiences over the course of its change in time there. Just like speed, an average speed is the change in displacement over a certain period of time, but not any specific time in itself. So this is our next formula. Hopefully that makes sense to you. Let's imagine that we have an object that starts, just to give you an example here, we have a car. So I'll go ahead and draw out a car here. Try to draw out a car here. There we go. And it starts out at a stop sign. Okay. There we go. And then after, let's say, 2 seconds, it's now over here. So we know that it's moved. And it has a speed. Now this would be an instantaneous speed of, let's say, 5 meters per second. I'll give myself a second sig fig here. 5.0 meters per second. Okay. So you're here, you're stopped at a stop sign, and then after 2 seconds, so this is t1 equals 0 seconds. And this is t2 equals 2.0 seconds. Okay. So my question for you is, how much acceleration does this car have? It's pretty simple, I hope. You can see that if the car is stopped right here, that its speed while it is stopped at that moment is 0. And so if we plug this in, we end up with the average acceleration. There we go. Being 5.0 minus 0. The pen is really acting up today. Over 2.0 minus 0 for an average acceleration of 2.5, right? Because 5 divided by 2 is 2.5. Now, what's the units on the top here? This is a little weird, so I just want to keep this. I want you to keep this in mind. The units on the top are meters per second because those are speeds, right? And the meters on the bottom are seconds because those are times. And so our units are actually meters per second, which is weird, I know. But that's the way that it is, meters per second. Now, just as a side note, this will come up often, so I want to show you how this works. This set of units is actually, it's correct, but it's the non-lazy way of writing it. There is a lazier way of writing it, and so many people will write it the lazier way. And I'll show you what that is. But to do that, you have to remember how to divide fractions. So really this means meters divided by seconds divided by seconds. And so if I wanted to write that as just a division problem, I would write meters divided by seconds divided by seconds over 1. Because there's nothing on the denominator of that, there's just a 1 on the denominator of that unit down there at the bottom. Now if you remember how to divide fractions, you remember you can't really do it this way. So what you end up having to do is change this to multiplication and then take the reciprocal here. And so we end up with meters per second times 1 over seconds. And so the answer for that, the simplified, lazy way of writing it, is meters times 1, which is meters, seconds times seconds, which is seconds squared. And so our actual units right there, if we're trying to be lazy, which I usually am, is meters per second squared. So acceleration always has this unit right here, meters per second squared. If you write it as meters per second, that's totally okay. I will do that too sometimes, so that's fine. Okay. Okay, now there's just very quickly, we're going to finish this up. There's actually 3 types of acceleration in physics, and so we're going to talk about those very quickly. Those 3 types are, all of them are acceleration, okay? So if you see someone or hear someone talking about an acceleration, they could be referring to one of these 3 possible situations, okay? The first is, 1 is speeding up. And my pen is really not good right now. There we go, speed up. There we go. The second is the speed is going down. Why is this the case? Why is that okay to say? Because remember the formula. The formula just says the change in speed. It doesn't say anything about which way the speed is changing. It talks about just the fact that the speed is changing. In this last piece, and we're going to talk about this later in the unit actually, is turning. So I'm going to write it in here, but I just want you to kind of hold on to the idea for a second, because we're not going to talk about it today. Turning. Now, why is that the case? Well, we're going to find out later on that in physics, speed is not the best thing to talk about. Actually, velocity would be. Velocity requires you to have a direction. So if you're going to be talking about acceleration is really the change in velocity, which means it could also be a change in direction. And so we'll talk about that more as time goes on. But any of those 3 could be an acceleration. In the real world, we often call this a deceleration, but there's really not that. There's not really nothing like that in physics, so we don't really talk about that. Those are all accelerations. You could say this is a positive acceleration and this is a negative acceleration as it slows down. That's totally fine. We'll talk, as I said, more about turning later on. Okay, very good. So with that, I'm going to go ahead and wrap things up. Don't forget to fill out those note sheets. I know they sometimes are not the best, but it will be helpful for you later on, I promise you. And then, of course, don't forget the interesting question form. If you're struggling to find questions, please make sure you watch the video in which I talk about what are good questions and what are bad questions to ask. Otherwise, just throw out there whatever you're having problems with, and we'll see if we can make it work for you. Okay, with that, I'm going to go ahead and sign off. If you have any further questions, don't forget you can always email me, or you can save them up for our discussions the next day in class. It's important that this stuff is discussed through because, again, displacement, speed, acceleration, we're going to use them for the entire year. So the better you understand them now, the better you're going to do for the rest of the year. Okay, with that, I'm going to sign off. Good luck. If you have any questions, let me know.